Welcome to Electronics Pariksha channel. Today we'll discuss few more problems from diode circuits of analog electronics. Okay. Now we'll see the first question. The capacitance of a full wave rectifier with 60 hertz input signal and peak output voltage VP. See, peak output voltage VP means it is nothing but a DC voltage, 10 volts, and load resistance R is equals to 10 kilo ohms. Input ripple voltage is VR is equals to 0.2. So it's telling there is a full wave rectifier. They have a full wave rectifier, and that is given to a capacitor filter and a load resistance across it, that is RL. Okay, so he's telling that a ripple voltage is there in the output voltage. Ripple voltage VR is equals to 0.2 volts, and the frequency of the input signal is 60 hertz. The output DC voltage, peak DC voltage, is 10 volts. Now he's asking for the capacitance. What is capacitance? Yeah, for the full wave rectifier, we have already derived the ripple voltage VR is equals to IDC divided by 2FC, which can also be written as V peak voltage 2FC RL. Okay, substituting these values, so the peak voltage is given as 10 volts, 2 into frequency is 60 hertz. Capacitance we don't know, so I will put C only. RL is 10 kilo ohms, 10 into 10 to the power of 3. So here ripple voltage VR is equals to, it is 0.2. So from this we can solve the capacitance. C is equals to 41.67 microfarads. So the answer is option C. Now we'll see the next question. The peak to peak ripple voltage of a half wave rectifier and a filter circuit operating at 60 Hz, which has a capacitance of 680 microfarads. And the average output voltage is 28 volt and load resistance is 200 ohms. So he's asking for ripple voltage here. There is a half wave rectifier similar to above problem, but here it is a half wave rectifier given to capacitor filter. Okay, this is load resistance of 200 ohms. This is a capacitance of 680 microfarads. So input frequency F is given as 60 hertz, and output voltage DC voltage is given as 28 volt. These are the parameters that are given. So now for the half wave rectifier, the ripple voltage is IDC divided by FC. See, for a full wave rectifier, it is IDC divided by 2FC. For the half wave rectifier, it is IDC divided by FC. You should remember these formulas, which can also be written as VDC divided by FC RL. Now substituting the values. VDC is 28 volts, frequency is 60 hertz, capacitance is 680 microfarads, and load resistance is 200 ohms. V ripple voltage, if you calculate, it will be around 3.43 volts. So answer is option B. Now coming to next question. The voltage transfer characteristics as shown in figure will relate to. See, if you observe the characteristic, it is like this. This is input voltage, y-axis is output voltage. It is linear up to certain limit. Okay, for entire negative cycle, it is linear. It is linear up to certain limit of positive cycle and remains constant after some time. So from this, if you draw the sinusoidal waveform, output sinusoidal waveform, it will be like this. The positive half cycle will not be complete. It will be clipped off to certain portion. This is the full positive half cycle, but it will be clipped off per certain portion. For remaining portion, everything will remain. Output will be equal to input. Okay, this is the output voltage from the given transfer characteristics. So it should be either, there are two chances. One is a peak clipper. It can be a peak clipper. Second thing, there must be a Zener diode which is maintained at this voltage level. Assume this is V voltage. For this particular voltage, if you place a Zener voltage, it stabilizes the output voltage. So it can be a voltage regulator. It can be a voltage regulator or a peak clipper. In the given options, voltage regulator is there, half wave rectifier and full wave rectifier is there. Half wave and full wave rectifier, there is no chance. So the option must be one only. So answer A. So we'll see the next question. A power supply uses a bridge rectifier with a capacitor input filter. If one of the diodes is defective, then so he's talking about a bridge rectifier. This is a bridge rectifier. This is diode D1, D2, D3, and D4. Okay. Here the load resistance is connected. But here, instead of load resistance, he's giving to a capacitor filter and then taking the load across the capacitor. This is RL. Okay. Now what he's saying is this is D1, D2, D3, and D4. If any one of the diode fails, what happens if any one of the diode fails? If say during positive half cycle of the input signal, which diodes will conduct? D2 and D3 will conduct. Okay. During the negative half cycle of the input signal, D1 and D4 will conduct. Both will conduct. So, if any one of the diode fails, if D2 fails, the positive half cycle input will not be there. Only negative half cycle will be there, like this. Output will have only negative half cycles. There will not be any positive half cycle. The positive half cycle of the input signal will not be converted into a pulsating DC voltage. Okay, when D1, D2 or D3 fails, if D1 or D4 fails, there will be only positive half cycles. There will not be any negative half cycles in the output. Means, in simple sense, if you want to tell, if any one of the diode fails, the bridge rectifier, the full wave bridge rectifier, will convert into a half wave rectifier. It acts like a half wave rectifier. It's very simple. Okay. So now what happens? He's telling if one of the diode is defective, then the DC voltage will be lower than its expected value. It's obvious. For a full wave rectifier, if you see DC voltage for a full wave rectifier and half wave rectifier. For a full wave rectifier, it is 2 Vm by pi. For half wave rectifier, it's Vm by pi. So option 1 is correct. The ripple frequency will be lower than its expected value. Obviously, ripple frequency for full wave rectifier is 2 times of input frequency. For half wave rectifier, it is same as input frequency. So it becomes half. So this is also correct. The surge current will increase manifold. This is also true. So the answer is option D. Like the video, share the video, and subscribe to the channel for better content and more videos. Next question. For the circuit shown below using ideal diode, the voltage and current are. Here he is telling the diode is ideal. So this is 10 kilo ohm resistor. This is plus 3 volt. Sorry. This is a diode D and this is minus 3 volt. So if the diode is ideal, it doesn't have any cut-in voltage, and the P type of the diode is connected to positive voltage and N type is connected to negative voltage. So diode D is on. It is in on state. So it acts like a short circuit and current flows in this direction. So the current I is equals to 3 minus 3 divided by 10 kilo ohms. That is 10 into 10 to the power of 3. So current I will be 0.6 milliamps. And he's asking to find out the voltage at this point. When the diode is short circuit, the voltage V is equals to minus 3 volts by applying KVL in this loop. If you apply KVL, this is V output. If you apply KVL in this loop, it will be minus 3 volt. So the answer is option A. If you see the next problem, the output VDC for the above circuit is. See, the circuit is half wave rectifier with a capacitor at the output. Okay. So here the capacitor will be charged to VDC because it is only one half of the cycle that flows here. If the input voltage is sinusoidal wave, the output will be like this, pulsating DC. But capacitor will be charged to this peak value. So that peak value we need to find out. So this peak value is nothing but Vm. So Vm we need to find out. So from the given circuit, input voltage is Vm sin omega t. So the output voltage across the capacitor, the output voltage across capacitor C will be equal to Vm. So here Vrms for given voltage is Vm divided by root 2. So Vm is equals to Vrms into root 2. So Vrms is nothing but 230 volts multiplied by root 2. Okay. Sorry. Actually here Vrms is 12 volts. We have to consider 12 because 12 volts is the secondary output, not input. The voltage across the secondary winding is 12 volts. So that particular voltage we need to find. We need to consider. So it is 12 root 2. Answer is option D. See, please here, I request you should not get confused here. Okay, for a half wave rectifier, Vrms is equals to Vm by 2. Why we have considered Vm by root 2 here? You may ask me. But that is for the output voltage. That is not for the input voltage. First, we need to find out V maximum that is appearing across the secondary winding. See, across this secondary, this particular part, across this secondary winding, what is the maximum voltage? We need to find out. That maximum voltage can be written as Vrms root 2. Okay. Here we are finding out 12 root 2 is the maximum voltage. That maximum voltage only will come at the output of the diode here. That particular maximum voltage only will come at the output. So that particular value will be stored in the capacitor. So that's why we are finding V maximum using this, not this. Okay, hope you have understood this concept. Now we'll see the next problem. When compared with a bridge rectifier, a center tap full wave rectifier has. So we'll see the bridge rectifier first. This is the primary winding. This is the secondary winding. Every time I draw this circuit, because this will be a great practice for you. If you're solving these problems parallelly with me, taking a notebook, this will be really a great practice for you and this will help you in your examinations. This is the bridge rectifier, whereas center tap is, this is a center tap rectifier. Center tap has 2 diodes, bridge has 4 diodes. This is center tap. If you see the differences here, when compared to bridge rectifier, a center tap full wave rectifier has higher transformer utilization factor. See, transformer utilization factor (TUF) for full wave bridge rectifier is 0.812. For center tap, it is 0.693. So he's telling that center tap has higher transformer utilization factor compared to bridge. That is wrong. Bridge has the higher transformer utilization factor. Second point. Here, center tap can be used for floating output terminals and no input terminal is grounded. See, in the center tap, if you see this center tap itself is a ground. This center tap here at this point, you can see this. This center tap itself is the ground. So you cannot say that no input terminal is grounded. And he's telling it can be used for floating output terminals. No, center tap cannot be used for floating output terminals. It can't be used. Whereas bridge rectifier can be used. Floating output terminals. Bridge rectifier can be used for floating output terminals. Okay. So this is also false. Center tap needs 2 diodes instead of 4. This is true. Center tap needs 2 diodes. Number of diodes in bridge rectifier is 4. Here it is 2. And center tap needs diodes of lower PIV rating. This is false. Bridge requires lower PIV rating because in center tap, what happens is when the diode is reverse biased, the voltage across the voltage across the diode will be 2 Vm. When the diode is reverse biased, suppose this diode D2 is reverse biased, D1 is conducting. When D1 is conducting, this is the Vm voltage across the upper primary winding, and this is Vm voltage across the lower primary winding. When the diode D1 is conducting, the entire upper primary winding voltage will appear across the load resistance. So the voltage across the D2 will be load resistance VL plus secondary winding voltage, that is Vm, which is equals to Vm plus Vm 2 Vm. So 2 times of Vm 2 times of Vm is appearing across the reverse bias diode. So it is 2 times of PIV. The peak inverse voltage should be 2 times of maximum voltage of the input. So PIV rating of the diodes should be higher for center tap. So this is also wrong. So only three. Third option is correct. So answer is option C. We'll see the next question. Which of the following components are chosen to construct a DC power supply to supply 6 volts DC voltage from 230 volts AC? Okay, the input is 230 volts AC. He wants 6 volts output DC. First, what happens? There will be a transformer. This is a transformer. Basically, this should be a step down transformer. Why? Because he needs only 6 volts DC. So here 230 volts will be there. 230 volts RMS voltage is given. Okay. So this transformer should be given to a rectifier. That is diodes. Basically, it is a diode. Half wave rectifier I'm taking. Then it will be given to the capacitors and the resistors, which acts as a filter. The capacitor and resistor, which acts as a filter. Then it should be given to a voltage stabilizer. That is nothing but usually we will take a simple voltage stabilizer, that is Zener diode, or in advanced systems you can take a 3-pin voltage stabilizer. This is the actual system. Okay. First, what will be there? A transformer will be there. This is a transformer, step down transformer. Step down transformer. Then it should be given to a rectifier. Here diode is acting like a rectifier. Then it should be given to a filter. Here capacitor and resistor are acting like a filters. Then it should be given to a voltage stabilizer, voltage regulator or stabilizer. Then you will get a stabilized output voltage, constant DC output voltage. Okay, this is AC input. So this is a circuit. So how it should be arranged? First step down, second diodes, that is rectifier, third capacitors and filter, that is capacitor and resistor, that is filter, fourth voltage stabilizer. So answer is option D. We'll see the next question. The silicon diodes are less suited for low voltage rectifier operations because, see, silicon diodes, the cutting voltage of a silicon diode is 0.7 voltage, whereas for a germanium diode, it is 0.3 volts. If you see the graph, it will be like this. The cutting voltage for a germanium diode is 0.3, whereas cutting voltage for a silicon diode is 0.7. So for a low voltage, if you use silicon diode, there will be higher voltage drop. Silicon diodes will give higher voltage drop at low voltages. So most of the voltage will be dropped. So they are not suitable for low voltage rectifier because it has got higher cutting voltage. 0.7 volts will be dropped. Okay. For germanium can be used for a low voltage. But if the input voltages are less than 0.3 volts, then germanium also will not function. What will be useful? You have to use op-amp rectifiers, operational amplifiers, which are also called as micro amplifiers. Okay. Now, yeah, the figure shown below shows the transfer characteristics of which one of the following. Same question we have seen in the beginning also. So the output must be a positive clipper. Here I would like to draw this. What will be the output voltage? How the output voltage look like? It will look like this. The positive portion will be clipped off. Output will be like this. This is nothing but a peak clipper. Okay. So the answer is option A. He has also given option B as bottom clipper. How the bottom clipper transfer characteristic look like? I'll draw that also. Bottom clipper means the bottom portion should remain should be clipped off. So here it should be remain constant. It should look like this. So now the output voltage is like this. The positive cycle will remain fully and negative cycle will be clipped off. This portion will be clipped off. This is called bottom clipper. This is bottom clipper. Okay. In the examination, he may ask you the match of following also. This is peak clipper. He may give you options as voltage stabilizer also. You can select that also. If it is two-side clipper, two-level clipper, as it is given in option D, how it look like? So transfer characteristic will be like this. So both sides you will see a constant parameter. The output voltage will look like this. Okay, this is a two-level clipper. Positive peak is clipped, negative peak is also clipped. So these three diagrams you have to remember. We'll see the next question. The figure shown is a circuit of which one of the following? See, obviously, when the two diodes and two capacitors are involved, it must be a voltage doubler. So this is a voltage doubler circuit. We have seen in the yesterday's class also, if two diodes and two capacitors are involved, it is voltage doubler. And here the output is connected. Output is taken across two capacitors. So it is a full wave voltage doubler. If output is taken across single capacitor, it is a half wave voltage doubler. So that is the basic difference. Single capacitor, if output is taken across single capacitor, that is half wave voltage doubler. Okay, we'll see the function. During the positive half cycle, what happens? During the positive half cycle, current flows in this direction, and the voltage across the capacitor C1 will be plus Vm. Okay. During the negative half cycle, the current flows in this direction, like this. And the voltage across the capacitor C2 will be plus Vm. Now the output voltage is Vm plus Vm. The voltage across two capacitors, that is Vm plus Vm, is equals to 2 Vm. Okay, so answer is option B, voltage doubler. Now we'll see next question. There is a waveform. Input signal is given as 10 volts positive peak and 10 volts negative peak. That is 20 volts peak to peak. That is given to this circuit. We'll redraw the circuit here. This is not a bridge rectifier because it has only two diodes. And there is a resistor 2.2 kilo ohms. And there is one more resistor 6.6 kilo ohms. Okay, output is taken across this. Output is taken here. And he is given diodes are ideal. So there is no voltage drop across the diodes. Now we'll observe the circuit. This is the input signal. During the positive half cycle, what happens? How the current flows? During the positive half cycle, plus and minus, the current flows in this direction, like this. Through the diode D2 it flows. The current flows. And some portion of the current will enter here also. Here also. Some portion of the current enters here also in this branch. This is during the positive half cycle. So if you calculate based on that, the output voltage will be, the output voltage is taken across the 6.6 kilo ohms. So first we'll calculate the current. So if you redraw the circuit for this, the 2.2 kilo ohms will be here, and 6.6 kilo ohm, and one more 2.2 kilo ohm branch will be here. The diode will act like a short circuit in this branch, 6.6 kilo ohm branch. It will be like this. So you want to calculate the current now. The current I will be, input voltage is 10 volts divided by 2.2 kilo ohms plus the parallel combination of 6.6 kilo ohms and 2.2 kilo ohms. This is the current that is flowing in the circuit during the positive half cycle. This is the entire current that is flowing. Okay. Now the output voltage will be, what is output voltage? The output voltage is nothing but the current multiplied by this parallel combination. The output voltage is nothing but the current multiplied with this parallel combination of 6.6 kilo ohm and 2.2 kilo ohm. Okay, because we need the voltage across this particular thing only. This is nothing but the output voltage. Here he is collecting the output voltage. So the current flowing in the circuit multiplied by this parallel combination. Okay, this portion is output voltage. So substituting all these things, current flowing is 10 divided by 2.2 kilo ohm plus 6.6 kilo ohm parallel combination 2.2 kilo ohm multiplied by 6.6 kilo ohm parallel combination 2.2 kilo ohm. So this entire thing is like the video, share the video, and subscribe to the channel for better content and more videos. So this entire thing is V out is equals to 4.3 sine omega t. This is for the positive half cycle. Okay. Now we'll see for the negative half cycle also. We'll read all the circuit. This is a diode and this is a resistance 2.2 kilo ohms. There is one more diode. This is 2.2 kilo ohms and this is 6.6 kilo ohms. This is the load resistance. 6.6 kilo ohms is the load resistance. So now during the negative half cycle, if you observe carefully, this is negative half cycle. So what happens? The current flows like this 2.2 kilo ohms, 6.6 kilo ohms, and through the diode D1 and this in this way, in this direction the current flows. Some portion of the current enters into this 2.2 kilo ohms branch also. So if you observe carefully, during the negative half cycle and during the positive half cycle, the current direction through the 6.6 kilo ohms is same. See here, during negative half cycle, it is going from right to left. Even in the positive half cycle, it is going from right to left. Okay. So there will be only positive waves in the output. There will not be any positive and negative wave. Only positive half cycles will be there. You can read out this circuit like this. So there will be a 2.2 kilo ohm and here the diode is short circuited and 6.6 kilo ohm. These two will be parallel combination and again there is a 2.2 kilo ohm in the lower branch and the current flows like this. Okay. So the calculations will be similar. Here also even you will get output voltage as 4.3 sine omega t. So during the positive half cycle and during the negative half cycle, you will get answer 4.3 sine omega t. So answer is option A. So in the output only positive half cycles will be there whose peak value will be 4.3 volts. Hope you understood this problem. We'll see the next one. So consider the above circuit V input is equals to Vm sin omega t. The output voltage V naught for RL tends to infinity. See, there are two diodes and two capacitors. You must have understood by this, by now. It is nothing but a voltage doubler. Anyway, we'll see the operation. This is the capacitor C1. This is the diode D1. And this is the diode D2. This is the load resistance RL. And this is the capacitor C. And from here, we'll collect the output voltage. Okay. Now, during the first, we'll see negative half cycle here. During the negative half cycle, blue color is negative half cycle. Diode D1 conducts and current flows through C1. Sorry. So there will be voltage develops across C1, that is Vm. Vm is the voltage that develops across C1. Okay. Now, next during the positive half cycle, this orange color is positive half cycle. Vm appears here. Current flows through diode D2 and capacitor C2. Because RL is tending to infinity, this acts like an open circuit. RL tends to infinity, that acts like a open circuit. And current flows through C2. So what is the voltage that develops across C2? It is voltage across C1 Vm and the input voltage Vm. So it is 2 Vm. So voltage across C2 will be 2 Vm. 2 Vm. So it is simply acting like a voltage doubler. Answer is option C. The output is connected across single capacitor. So it is half wave voltage doubler. of a voltage W. Now we'll see the next question. In the given circuit, D1 is a ideal germanium diode and D2 is a silicon diode having its cutting voltage as 0.7, forward resistance is 20 ohms, and reverse saturation current IS is 10 nanoamperes. So, what are the values of I and V for this circuit? So, whenever the silicon and germanium diodes are connected in parallel, first germanium diode connects because its cutting voltage is very less. Silicon diode cutting voltage is 0.7, germanium is 0.3. So, lower cutting voltage diode will connect first. Okay, the higher cutting voltage diode will remain open. So here in this branch, the germanium diode whose cutting voltage is 0.3 practically, but here he is telling it is an ideal germanium diode. So the voltage drop across it will be 0 volts. So germanium diode is on and the silicon diode will be off. So current flows like this through the germanium diode. So the voltage across this particular branch is 0 volts. So output voltage is 0 volts and current flowing is I is equals to 6 divided by 100, that is 60 milliamps. So answer is option A. Hope you understood this session, the problems. Please like the video, share the video and subscribe to the channel for better content. We are putting a lot of efforts to bring this content to you. So we request only one thing, just subscribe the channel, like the videos and share the videos and support us in the best possible way. Okay, thank you very much. Sri Raghava Academy online coaching center for the regular and backlog students dedicated to diploma and engineering courses. Semester wise and subject wise coaching is available. Contact the number 70192 46753.